I don't know. Maybe it's the weather. Maybe it's the fact that there's a mini exam due today. I don't know. There's probably like 6 people in the tutoring lab right now helping each other. Just put that right there, please. Thank you.
So it takes a whole week to put in a door.
What kind of door?
Car door. Like a new car door.
Sounds about right.
Yeah.
You got to wait for the parts to come in.
Yeah, well, my wife's a little pissed because some lady at the grocery store, like, we were waiting to get out of traffic, and she just backed up into us. Like, we honked and everything.
Oh, I had that happen here.
She, like, honked everything, tried to get her attention.
Yeah.
Nope.
I was about to pull out of the parking spot here, and a lady had gone past me, and then a car was backing out, and she wanted that spot, and I was already coming back, and she just backed up right into me. I was honking and nothing. Excuse me, I'm just, not that I don't like light, but it messes with my video a little bit.
I shut down like 8 pages of notes down to like 3.
All right, well, it's just about time. If you've got your mini exam, please place it here, hand it in.
So your online lectures have been helping out my niece.
Oh, good.
She's at Colorado State University.
Oh, yeah?
And she's in
Okay, anybody else? Last call. Did you spell her name wrong?
No.
All right.
All right, everybody. Y'all doing good? Seems a little like there's more elbow room in here today. All right, well, we need to keep moving. Last time, you all had a great time. I could tell that you really enjoyed the chain rule.
Sure.
So we move on. 11.6. And also keep in mind something here. Our goal is to get through chapter 10, 11, 12, and 13. That's the goal here for this class. I hope that somewhere near the very end of the semester, I will close the book and say we're done with this textbook, which we should do, all right? So we're still in chapter 11, right? We're not quite at the midway point of the semester yet, though. So, all right, directional derivative, 11.6, and the gradient vector. I love this section because it's very visual, and it has a very, very cool result. Like what comes out of this at the end is very, I don't know, it's kind of amazing when you think about what we're able to determine here. So we're going to go back and look at a surface. I'm about to show you something here. That's why I have the light turned down a little bit. I'm going to look at this surface, and what I want us to realize is that if you have a surface and this surface is a function of 2 variables. So z equals f of xy. We can pick a point xy, plug that into the function, and it spits out a point on the surface. So we can pick any point in the domain and get to a point on the surface. At that point on the surface, imagine yourself standing on the surface of, or standing on the surface, and then you can pretty much turn in any direction and start walking, right? And in that direction that I walk, there is a line that is tangent to that surface. In that particular direction, there's a tangent line. The slope of that tangent line will depend on what direction we're pointing in, because the surface might do different things in different directions. So here is a visual of what I was just saying. All right, so here's a surface, okay? And ignore the red arrows for now. You see the big old black dot on there? That's the point that we're at on the surface. So we've plugged in some x and y, and it spit out this z, and that's where we're standing. Now I can move that point around, so I can get ourselves to a different point on the surface. This is very sensitive here. Okay, there we go. So I'm at that point. And now that I'm at that point, I need to kind of turn in some direction. And we're just going to pick an arbitrary direction. Now when we say that, like how are we going to determine direction? Where do we, what's 0 degrees? What's 20 degrees? So what we do is we try and look at this from the top down. Okay, so if we look from the top down, where is my x-axis? Let me see, hold on, I need to see, my angle is 0. So actually, the x-axis, this is the x-axis right now. All right, can you all see that? This is the x-axis. I'm standing up here on that surface. So if I just look from the top straight down, okay, it's going to be hard to get this straight down. But there's my x-axis, right? And I'm pointing right now, that black dot's supposed to be right on top of that red dot. So if I look down at the ground, if the surface were transparent, I would see a little red dot down there. And then that arrow corresponds to the direction that I'm pointing. So that would be 0 degrees. Understand? And now let me change the angle a little bit. So now see, I'm pointing in a different direction. I was trying to get this to all fit on one thing so I could change things and you could see them. So yeah, that'll work. You all still see that okay? My angle's too far away. Go a little smaller here. Hey, why didn't it like that? There we go. So now you can see that's good, right? Now you can see the angle changing. Now I also did another vector at the origin. And the reason I did a vector at the origin is just so you could see the angle I'm talking about is the angle between the x-axis and the vector. Got it? All right, so now it's time to actually start taking a step in that direction. So I've picked that direction right there. Let me kind of, yeah, this will be good. So I'm gonna start walking in the direction of the red arrow. And when I do that, I'm basically cutting through the surface with a plane. And that plane is pointed in the same direction as that arrow, right? And when I walk along that, I'm actually going to be walking along that blue curve, aren't I? Come on, geez. There we go. Sometimes it's hard to control. Okay, so I'm going to start walking along that blue line, and that's going to be in the direction of the red. And when I take that first step, that's going to be my derivative, right? It's the derivative of that blue curve. So let me show you the tangent. Boy, didn't like that. There it is. It's kind of hard to see it, but do you see that blue line right there? Yeah. That's our tangent line. I'll take the plane out. Now you can really see it. And then if I start walking, then I'm going to have tangent lines at every single point. Now, let's see what happens if I change my angle. Right now, I have the computer computing the slope here. I know this is very difficult to see back there. Right now, if I were to start taking a step in that direction, I'm going to go down, right? And the slope is actually negative 0.64. That's a negative slope. So what would happen if I change my angle and point the other direction, like 180 degrees, turn around? It should be positive. Let's see if I can do that. I'm going to try and turn that around. I don't know. I'm kind of guessing here what that angle was. But if I do that, oh, hey, I did pretty good there, didn't I? Positive 0.64, right? So at every angle, I'm going to have a different slope. So recap. We go to a surface, we pick a point, and pick any direction, and we should have some slope defined in that direction. The question is, what is it? How do we compute it, right? Okay. Anything else I want to say here? Show tangent. If we have a tangent line there, we also should have, well, should we have a tangent plane there? You tell me. If I'm pointing in some direction and I start walking, I'm going to have a tangent line. Is there a unique tangent plane at that point? You would need another vector, wouldn't you?
Yes.
To get it? Because you need two vectors and then cross them to get the normal for a plane? Okay. All right. Let's move on. Here's the formula. If z equals f of x, y, right? If z is a function of two variables, then f has what we call the directional derivative. So this derivative that I'm referring to is called the directional derivative. That makes sense, right? It's a derivative that is based upon the direction that you're pointing. F has a directional derivative in the direction of the unit vector u equals ab. And that derivative is defined as follows. Okay. So you remember that red vector that was on the ground? That gives us our direction. There's something very important about that red vector on the ground. If you're going to use this formula, that vector on the ground has to be a unit vector. That's the biggest mistake students make when they try to use this formula, is I give them a vector and tell them, hey, find the directional derivative pointing in the direction of this vector, and they forget to make a unit vector out of it, because you have to start with a unit vector. So you have a unit vector AB, and then here's what it is. Here's the notation. D subscript u. This means the derivative in the direction of u of the function of x, y, and it's equal to, do these look familiar? This right here. It's the partial of f with respect to x, right? And then you're scaling it by the first component of the unit vector. And then the partial of f with respect to y and scaling it by the b component of the unit vector. This answer, whatever we get, will be a number, and it represents the slope of the tangent line to the surface in the direction of the vector u. Okay. Just wondering if I should talk about this formula a little bit before we do an example. Let's do an example first, then I'll talk a little bit more about this formula. All right, if z equals f of x, y is equal to x cubed, if you're just coming in, the test, yes, test? Anyone else? Okay. Z equals f of x, y equals x cubed minus 3xy plus 4y squared. Then find the directional derivative at the point 1, 2 in the direction of a vector making an angle of pi over 6 with the x-axis. So let's start out by trying to find u. All right? Let's try and find the vector u. The vector u is the direction vector, right? Don't confuse that with direction vector of a line. This is the direction in which we want to point in, all right? So we're going to walk out to this, we're going to walk out to 1, 2, go up on the surface to the point, and then pivot around until we're pointed in the same direction as this vector u. Now that vector u has to make an angle of pi over 6 with the x-axis. So here's pi over 6 is about like this. 30 degrees. our vector u has to be pointed in the same direction as that. Pardon? Okay, so you can go back to your knowledge of the unit circle, right? The unit circle, if this has to be a unit vector, then if this, we can say this point right here lies on the unit circle, then we know the x and y coordinates of that point. What are they? I heard. Root 3 over 2 and 1/2. So I could use that as my vector, root 3 over 2 and 1/2, and I'm guaranteed that that's a unit vector. I mean, I could check it myself, square each component, take the square root, you should get 1. But just knowing about the unit circle, I know that already, right? So that's my vector. Any questions on that? Okay, now, next point, or next thing is,
Are you using cosine and sine for your x and y?
pardon?
You're using x and y for you're using cosine and sine for x and y. Is that correct? To get the unit vector.
Cosine, yes.
So you just plug in the cosine and sine.
You can get these two by doing cosine of pi over 6 and sine of pi over 6. Yeah. All right. Okay, I want to make sure we're all kind of seeing what's happening here. In three-dimensional space, here's x, here's y, here's z. We have some surface up here. We're going to walk out to the point 1, 2. So we're going to go out 1 unit on the x-axis, 2 units on the y-axis. That's the point 1, 2, right? We're going to plug it into the function, and we're going to be somewhere, right? Up here? So that's somewhere on this surface. With me? Once we're standing up there, we need to point in the vector in the direction of this vector. So that vector makes an angle of pi over 6 right here. That angle is this angle. So imagine moving that vector over here so that when you're standing up there, looking down, you see a little pi over 6. Does this make sense or not? You sure? Look, if I'm standing up here, I could be looking out so that I'm looking parallel to the x-axis, right? But what I'm doing is turning by pi over 6. Now when I walk out, start taking a step, what's the rise or the drop going to be? That's my directional derivative. So now the formula. If you're just coming in, you need to turn in the, if you have it, turn it in. Okay, the formula is that the directional derivative in the direction of the vector u of the function f of x, y is equal to a times the partial of f with respect to x at x, y plus b times the partial of f with respect to y at x, y. Okay, that's what it is. Now, let's do some partials. We're going to need partials here, aren't we? So let's go ahead and compute them, and then we'll use them over here. So let's take the partial of f with respect to x. That's going to be 3x squared minus 3y. And that's it. Okay. What is the partial of f with respect to y? Negative 3x plus 8y. Everyone okay with that? And we know that the vector u was root 3 over 2, 1/2. So this is your A and this is your B. And so I'm ready to actually compute this. So here's what I'm going to do. The directional derivative in the direction of u of f at the point, what's my point? 1, 2, right, is equal to A, right, which is root 3 over 2 times the partial of f with respect to x at 1, 2 plus b, which is 1/2, times the partial of f with respect to y at 1, 2. Which is root 3 over 2 times what is the partial of f with respect to x if I replace x with 1 and y with 2? X with 1, y with 2, you should get negative 3. You should get 3 minus 6, right? Negative 3 plus a half. And then now go to the partial of f with respect to y, plug in 1 for x and 2 for y. 13. So this is negative 3 root 3 over 2 plus 13 halves. And that's, we could get one single denominator here. 13 minus 3 root 3 over 2. That would be a very clean, exact answer, right? No rounding or anything. And then we could also get the decimal. I haven't worked it out to get the decimal. Do y'all want to work it out or no? No? Is it positive or negative? Positive. It's positive. You can kind of tell because root 3 is smaller than 2. And 3 times 2 would be 6, and 13 minus 6 would still be positive. So this is a positive number, which means that as we walk in that direction, we'll be going up. Question?
Yeah.
Yes. Uh-huh.
So that 1 and 2.
Yes.
Are those just arbitrary numbers?
That was given here, right? That we were at the point 1, 2. So had we been somewhere else, we would just replace it with wherever else. Okay? Good. Anyone else turning in? If you're turning these in after 11 o'clock, I'm counting them late, but I'll still take them. Does this seem pretty straightforward? Yeah? Thanks, Sarah. It's 4.5 something? Okay.
So we're kind of like using the same formula before, right?
Yes. Okay, so let's talk about this formula. That's what I was wondering if we should do an example first or talk about the formula, but I think we get one example under our belt. Now let's go back and look at this. Do you remember when we did last class the partial of f with respect to y? I mean to x. We said that means we're going to hold what variable constant? Y. We're holding y constant. So if we hold y constant, then what that was really doing was slicing through our surface with a plane. And that plane was parallel to which plane? I'll try and draw the picture. Here's x, here's y, here's z. So if I hold my y constant, I'm slicing through with a plane that's parallel to the xz plane, isn't it? And that means I'm pointed in what direction? The same as the x-axis. And what is a unit vector that points in the direction of the x-axis?
1, 0, 0.
You would have u is equal to 1, 0, right? That's what you would have? You're thinking three-dimensional, right? So that little vector that's on the ground would be pointed in this direction. Do you agree? Now, what would our formula turn into if I said, hey, find the directional derivative in the direction of u of the function f of x, y, but using this vector? It would be 1 times partial of f with respect to x, right? Plus 0 times partial of f with respect to y, which means this goes away, and all it is this, right? So the partial of f with respect to x holding y constant is actually just a specific case of this formula where you're pointed out the x-axis. Now what would happen if I change it and this time I do the partial with respect to y? You hold x constant, right? And that means that you're going to be slicing through with the plane that's this way that points in the y direction. And that's going to be the vector 0, 1 instead. And then that's going to kill off this one and give you this one. So this is the more general formula for derivatives, partial derivatives, because it allows you to adjust the angle. Make sense? Yes.
Does this equation expand for the z-axis as well?
Yes, it does.
Like we'll have f, f's of respect to x with f of y. Well,
Yep.
f respect to y.
Yeah, I'm actually going to put it up. We'll do it. Yep. What we did right now, the reason we did this one first is because right now our function f has two inputs, right, and one output. And so it's a surface. And we can visualize it. And I could like make that thing turn and have little cute arrows and everything like that. But if we want to extend this idea to a function of three variables where you have f as a function of x, y, and z, then you don't have, I can't visualize it. I can't show it to you, right? But you still have the same concept. You can still compute a directional derivative. It's just not going to be easy to show you. So that's why we don't do it right away. How about this one? If z is equal to f of x, y equals the natural log of x squared plus y squared, then find the directional derivative at the point 2, 1 in the direction of the vector u equals negative 1, 2. So we're going to need partial derivatives, aren't we? We may as well get the partials now. All right, so the partial derivative of f with respect to x should be one over all that, right? Because derivative of natural log of something is 1 over it, and then times derivative of what's inside with respect to x. 2x. So you just get 2x over x squared plus y squared. So that's the partial with respect to x. The partial with respect to y, same thing, but 2y on top. Okay, I've got those. Now, can I go to the formula now? Why not?
You have to make sure that's directional.
Yeah. Is that direction vector u, is it a unit vector? And it is not. How can I check to see that that's not a unit vector? I can find its magnitude. What's the magnitude of that u? Square root of negative 1 squared plus 2 squared, which is root 5. That's not 1. So that's not a unit vector. How can I come up with the unit vector that points in the same direction? Divided by its own length. So I'm going to create a new vector and be sure that it's unit length. So I can't call it u, right? Because u is already being used here. So I'm going to call it v. The vector v that I'm going to use is going to be the vector u divided by its own length, which is really just negative 1 over root 5, 2 over root 5. Now I have a vector that points in the same direction but has unit length. And now I believe I can compute the directional derivative. The way I should write this is that I'm finding the directional derivative in the direction of what? V, right? Of the function f of x, y, right? And that should be equal to negative 1 over root 5 times f, partial of f with respect to x with what plugged in? The point 2, 1, plus b, which is 2 over root 5, and then the partial of f with respect to y with 2, 1 plugged in. That's what I was saying earlier. The unit vector, the biggest mistake I see people make is that they don't bother doing this. And so they just put negative 1 here and they put 2 here, and then it's incorrect. Must be a unit vector. That's the type of thing you don't want to get caught on an in-class test with a problem like this and forget that, because that's a huge mistake. All right, now we're going to plug in 2, 1 into the partial with respect to x. We're going to plug 2, 1 into the partial with respect to y and see what we get. So negative 1 over root 5 times 2 for x, so 4 on top and 5 on the bottom, plus 2 over root 5, and then plugging in 1 on the top, so 2 over 5. We have the same denominators there. Ooh, it's 0. This is negative 4 over 5 root 5. This is positive 4 over 5 root 5, and they cancel. So it's almost like back in Cal 1, when the derivative was 0, what did that tell us? We could be at a maximum. We could be at a minimum, but we could also not be at a max or a min. So like in Cal 1, if you had something like that, the derivative is 0 there, like this, derivative is 0 here, but you could also have this happen where your derivative is 0 there. So derivative being 0 doesn't guarantee that we have a max or a min, but it's a point of interest, right? We called these critical points back in Cal 1, wherever the derivative was 0 or undefined. So where the directional derivative is 0, well, that might be an interesting point, right? That might be something we want to investigate further. All right. We are, okay, one of the things that we are going to do is, and it's in this chapter, one of our main goals is that we have these surfaces and we want to find where they have maximums and minimums. It's a much harder process when it comes to surfaces than it was back in Cal 1. But that's one of the main goals. All right, moving on. All right, now we define what's called the gradient vector. Notice in this formula for the directional derivative that this is a times, not dot, right? That's a times that, and then it's b times that. If I just felt like it, couldn't I rewrite this right here using this notation? So what I say is, I'm going to have a vector. It has the partial of f with respect to x in it, has the partial of f with respect to y in it. Those are the two components. If I dot that with AB, then the dot product says this times this, right, which is that, plus this times this, which is that. So this is just another way of notating that directional derivative. Agree? Which I could then notate this way, because remember, the vector AB is the vector u. So this is a new little, this is like a condensed notation for that computation. You're taking your partials, creating a vector out of them, and dotting it with the unit vector u. So the directional derivative can be seen as a dot product. If you so desire, you could do this. Now, the gradient vector. We use this notation right here, which is
Capital del.
del, capital del. So you have del of the function f of x, y. This is, when you see this notation, when you see this capital del in front of the function, what it means is that you're going to create a vector, and that vector is going to contain the partials of the function. Partial with respect to x, partial with respect to y. That was that piece that we just had, just a second ago. That's this right here, okay? That right there. We now have a new symbol, a new notation for that, and it is this. Now you can also write it just del f. If you write del f, it's understood to be this. Do y'all get that this is just notation? That's all this is, notation. So what is the gradient vector? It is a vector that is determined by the partial derivatives of a function. So you give me a function, and then someone says, hey, give me the gradient of that function. What you're going to do is create a vector that contains its partial derivatives. So we can just practice real quick. If z equals f of xy equals e to the xy plus cosine x plus y, then find the gradient vector. So they want us to find the gradient of f. which by definition is the partial of f with respect to x, partial of f with respect to y. Now, why is it a two-dimensional vector? It's two-dimensional because I have two input variables, right? X and y. So f depends on x and y, two variables. That means I'm going to have two component functions when I do the gradient. Now, what is the partial of f with respect to x? So what's the derivative of e to the xy? Y e to the xy plus minus sine x plus y. And then the derivative of what's in here with respect to x, right? Which is just 1. So that's it. That's our partial with respect to x. What's the next component function?
F of y.
Okay, partial of f with respect to y, which will be x e to the xy minus sine of x plus y again. Close the vector off. I don't know if that's coming out, but oh well. That's it. That's the gradient vector. This is it. Now, if I wanted to know the directional derivative in the direction of some vector, like let's say I gave you this vector, root 2 over 2, root 2 over 2, and I call this u. If I said, hey, go find the slope of the tangent line if you're pointed out in this direction for that function right there, and I give you some point to go look at, then all you're going to have to do is take this vector and dot it with this vector. That's what you're going to do, right? Dot these two together. And then you basically get back to the other formula. So you might be asking yourself, why in the hell are we, why do this, right? Like, we just had a nice clean formula, why are we turning it into a dot product? Like, what's the point?
What do we get when we dot?
You get back to the original formula, which is the directional derivative. So I gave you the directional derivative formula and turned it into a dot product, and you should be asking yourself why. Like, why go through this trouble? Are you not? Do you not care? All right, well, I'm going to answer the question. But before we do that, we need to extend the ideas here of the directional derivative and the gradient vector to higher dimensions. So now this is where if we have a function of three variables, x, y, and z, then f has a directional derivative in the direction of the unit vector. This time, look at our unit vector. It's three-dimensional because our input, three different variables, so our direction vector needs three components. And look at the formula. The directional derivative in the direction of u of the function of x, y, z is a times the partial of f with respect to x plus b times the partial of f with respect to y plus c times the partial of f with respect to z. And if we had a function of four variables, then we would need a unit vector that had four components. And then the directional derivative would be the four partials scaled by the four pieces of the unit vector. If we had five and so on and so forth, there's no real limit. But in all of these, you could rewrite the partials using this notation and create what's called the gradient vector. So this, since our function has three variables, the gradient vector will have three components. It's just the three partials in a vector. Yes? Okay? All right. Again, why do we want the dot product? That's weird. But before we do that, let's do an example. If f of x, y, z is x over y plus z, then find the gradient vector and then the directional. Hold on, before we do this, I have a question. In the first example, we started with a function of two variables, and I said it's a surface. And then you go up to this point on the surface, and you point in a direction, and then you start walking, and the directional derivative gives you the slope of the tangent line. If you have a function of three variables, said I can't visualize that, but what would the direction vector mean? This is really weird.
It's just another variable. It's just another variable.
Yes.
Is it
So you're going to plug in, you'd have to plug in a point, right? And then before that point you plug in, and then it takes you to a point on the surface, right? So we had 2 dimensions for the point going in, 1 dimension for the point coming out. That height was the value of the function there. And then we pointed into a direction, started walking. Here, if I give you the input, that input lives in 3-dimensional space, right? Then the output lives in some other dimension. So it's impossible for me to talk about walking in a certain direction. So I'm going to do it a little differently. Let's say that we have a way of measuring the temperature very, very accurately at every single point in this room. All right? So right here at this point there's a temperature, and right here there's a temperature, and it's going to be a little different, right? And at this point there's a different temperature, and every point in this room has a different temperature. Yes? So this function of 3 variables that I'm just making you think of takes as its input 3 things. Let's say your position, x, y, and z in the room. And the output is the temperature at that point. Understand? Yes? So, if we are talking about the directional derivative, then what we would be doing is saying, okay, be at this point and then point in some direction. So I would have to give you a unit vector, and that would be 3-dimensional, wouldn't it? So it'd be in 3-dimensional space. So it'd be somewhere here. And then start walking that way. And when you walk that way, the directional derivative would give you what? The what? The rate of change in temperature as you move in that direction. That's what it would give you. So even though I can't really visualize it like a surface and up and down like that, we can still think about it that, with the idea of temperature. And that's pretty cool. Now, once you have 4 inputs, and then you start having to kind of wave your hands at it a little bit. Yeah, because you can't even visualize like where you are to start. And then what does your unit vector in 4 dimensions look like? Okay, yeah, we won't mess with it. All right, first thing, find the gradient vector. So what is the definition of the gradient vector? In this case, it's just what? It's a vector. It's the partial of f with respect to x, partial of f with respect to y, and with respect to z. If I can create that vector, then I have created the gradient vector. Now let's see if we can actually do this. What is the partial with respect to x? This might be a little bit messy. Just 1 over y plus z? Why? I don't get it. Yeah, because you're looking at that as 1 over y plus z times x. That's the way you can look at that function up there. And if like this is all a constant, right? Then derivative of x is 1, so your answer is just this. So the partial derivative of f with respect to x is pretty straightforward. How about the partial derivative with respect to y? That's going to be a little bit harder. Let me try it this way. Partial of this with respect to y means I need to treat x and z like constants, right? And what I'm going to do is I'm going to choose to do this with a quotient rule. So what would the derivative of this be using like a quotient rule? Derivative of the top with respect to y, that's a constant, so that would be 0, times the bottom, that's not going to matter. Right? Minus derivative of the bottom with respect to y. Just 1. Derivative of y is 1, derivative of z is 0 because z is a constant. So 1, and then times the top function x over the bottom squared. So the second component is negative x over y plus z squared. Understand? You could have brought the bottom up and then used chain rule, power rule, like as a negative 1 exponent, and then yes, that would have worked also. So I chose to do a quotient rule. Yes? Yeah, for z it's going to be very similar, isn't it? If I were doing this partial with respect to z, I'd still get 0, I'd still get this, minus, then when I did derivative of the bottom with respect to z, I'd still get 1, then I'd still multiply by the top, and then I'd get that squared again, right? So it's identical. Okay, that's my gradient vector. Now, find the directional derivative at the point 4, 1, 1 in the direction of u is 1, 2, 3.
You're gonna have to change your U.
I'm going to have to make sure u is a unit vector. It's not.
It's the square root of 14.
So the length of this is the square root of this squared plus this squared, which is
Square root of 14.
root 14. So I'm basically going to create a new vector v. It's going to be u over its own length, which is 1 over root 14, and then 2 over root 14, and 3 over root 14. So the directional derivative in the direction of v of the function f at the point 4, 1, 1 is equal to this dotted with this, right? But when I say this, I have to replace x with 4, y with 1, and z with 1. So can we do that? I'm going to leave it as a vector. I'm going to take this, replace y with 1, z with 1, so we should get 1/2 here. What happens if I replace x with 4, y with 1, z with 1? Negative 4 over 1 plus 1 is 2 squared 4, so negative 1. And then we should get the same exact thing here, right? Negative 1. Does everyone see I'm taking, this is the gradient vector evaluated at the point, 4, 1, 1. And then I'm going to dot that with 1 root 14, 1 over root 14, 2 over root 14, and then 3 over root 14. And then do all that, and that's your answer. So we'll do it. We've come this far. We should get 1 over 2 root 14 plus these two multiply, but that's going to be a minus 1 over, 2 over root 14. And then another minus, but this time 3 over root 14. You okay with that? Dotting? Get a common denominator?
Well, you can just put 2 and 3 together, and it's negative 5, and then find the common denominator.
I could do it now or later. I'm going to do 2 here and make that a 4. I'm going to do 2 here and make that a 6. And then just put all my numerators together. 1 minus 4 minus 6.
Minus 10 minus.
What's that? Negative 9?
Yeah.
Negative 9 over 2 root 14. So I have a negative rate of change in that direction. Any questions?
So the gradient vector, is that just so you can clean up the formula?
No, because I think it kind of made it worse, actually. Because the formula, the way it was presented, would have been fine. I mean, why not just keep doing that, right? You're about to see why that notation is useful, right? All right. So I'm going to go back to the first example we had where we're standing on a surface, right? Because I think that's the easiest to visualize. Standing at some point on a surface, we can point in any direction, and we start walking, we can get the rate of change. What would be a very profound question to ask if I'm standing on the surface and I'm sitting here going, what would be a profound question? What the hell are you doing there? Like, I know that's profound. Like, why? Okay, we're not going to get. But what would be something that would be pretty remarkable if I could just like figure out? Okay, like a max. So maybe, like, what direction do I point in for the steepest tangent, right? I mean, because I can just point, calculate, get a number. Point, calculate, get a number. Point, calculate. I can do that for, how many different angles are there? Infinitely many, right? So I could do that for the rest of my life and keep comparing and try and find the biggest and smallest, right? A profound question would be, can you actually tell me the direction that I should point in to get the steepest descent? Guaranteed, the steepest. And is it easy to do or not? This is where the dot product's going to come in. So remember this about dot products? That when you have the dot product between two vectors, that it is equivalent to the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between them, right? Now, with our idea of the directional derivative, the notation that we have is that the directional derivative, which gives us the slope of the tangent line in that direction u, is the gradient vector dotted with u, right? That's the notation that I created, and it seemed like, why do that? But if we rewrite it using that formula, then it becomes the magnitude of the gradient vector times the magnitude of the vector u times cosine of theta. But we know that the magnitude of u is 1 because it's a unit vector, right? Yes? So that doesn't need to be there. So the directional derivative, right? This is the directional derivative. That's the slope of the tangent line, is equal to the gradient vector times cosine of theta. How can you make this gradient vector the biggest it could possibly ever be? You would need to make this what? 1. Because cosine is going to be between -1 and 1. To make that as large as possible, you want cosine to be 1. What's the angle that corresponds to that? 0. What does that mean?
You need to be in the direction of the gradient.
That's right. That means that if you're sitting there and you jump up on the point on the surface, you're like, which way do I point, right? Which direction do I point in? What should u be? This is telling you that u should be in the same direction as the gradient vector. Because if they're pointed in the same direction, you're going to get the maximum directional derivative. That means that the gradient vector is the direction of the maximum rate of change. And that is crazy. But you wouldn't have been able to see that if you had not turned it into a dot product. So, which means the angle between the gradient of f and u must be 0 to attain the maximum, to attain the largest directional derivative. So remember, when you jump up on that surface and you're standing at the point, you're asking the question, which way do I point? And I'm telling you that the direction you point needs to have the same angle as the directional, or as the gradient vector. If you can do that, then you've got it. So that means you're just going to point in the direction of the gradient. Let's see if this can come together with an example. That's the profound result of this section. So maximizing the directional derivative. The maximum value of the directional derivative is the magnitude of the directional derivative. Because remember, that formula, if we can force this to be 1, if we can force this to be 1, right, then the directional derivative, which is what that stands for, is just the magnitude of f. Magnitude of the gradient of f. So this is saying the maximum value of the directional derivative is the magnitude of the gradient vector, and it occurs when we point in the direction of the gradient vector. It's awesome. So here's a surface. We want to find the direction as an angle of the maximum rate of change at the point 0, 0. So we're starting off on the ground at the origin. We're plugging 0 in, 0, 0 in. We go up to the surface, right? And now you need to tell me the angle that I need to point relative to the x-axis on the ground so that I get the maximum directional derivative. So what are you going to do? What are you going to do? What is the direction of the maximum rate of change is going to be the gradient vector, isn't it? So you need to find the gradient vector. Let's find the gradient vector. Now we need the gradient vector. Let's do the gradient vector first. That should be a two-dimensional vector. And it's the partial of f with respect to x and then the partial of f with respect to y. So what is our partial of f with respect to x? Cosine xy times the derivative of what's inside with respect to x, which is 1, minus sine x. And that's it, right, for partial with respect to x? Now, partial with respect to y? Negative cosine of x minus y. And then that's it, right? It's negative because when you take derivative of sine, you get cosine of x minus y. But when you take derivative of the inside with respect to y, you get negative 1. That's why that negative 1 pops out. So that's our gradient vector, right? Now what we need to do to find the direction is to actually look at the point that we're interested in, right? This is the point. That's going to tell us where we're standing on the function. Right now, this will give us the direction to point in, but it needs to know where we are on the surface. So we plug in 0, 0. So the gradient vector of the function at 0, 0 is equal to cosine of 0, 1 minus sine of 0, 0. So 1, comma, negative 1. That's it right there. 1, negative 1. Now we have not answered part A. Part A says find the direction as an angle. We found the direction as a vector. I'll try and draw this three-dimensionally first. Here's x, here's y. We have some surface up here, right? We went to the point 0, 0, which was the origin. We went up onto the surface, and we said, what direction do we need to point in order to get the maximum rate of change? And what we determined is that what we should do is we should go point in the direction of the vector 1. Here's 1 out the x-axis. Negative 1. Here's negative 1 on the y-axis. So we need to be pointing in a direction like that. Okay, so if we're standing up at the top, we look down, right? We should be pointing in that direction. And if we take a step, we're going to get the steepest rate of change we could possibly get. We're going to figure out what that rate of change is in a second, but let's get that angle. So if you draw the xy plane here, the domain of this function on the ground instead, two-dimensionally, we went out 1 here, we went down 1 here, and your vector goes like this. And what is that angle? You could say negative pi over 4. You could also go all the way around, but I'm just going to say this angle right here, negative pi over 4. You could say 7 pi over 4. That would be fine. Any coterminal angle would be okay. So the answer to part A, negative pi over 4. Make sense? Just out of curiosity, what would have happened if this would have turned out to be the vector 1, negative 2? Then when you drew it, it would be like this. 1, then negative 2. Your vector would be like this. How would you find this angle? You don't have to make a unit vector for this. Yeah, use some trig functions here, because this is really like a little right triangle or something. You could look at it that way. You know that has this side, this length is what? Like, you could say negative 2 and here is 1. And to find this angle, you could use some trig, arctan or something. Yeah. Okay, but yeah, you would have to mess with it. You have to be careful with domains. There's like 3 different ways you could get that angle, but I expect that everyone could get that angle. This one just worked out because it was, same distance down and over. It's 45, and you just need to figure out where you are. All right. So what is the maximum rate of change?
So when we find the angle, do you want to degrees or
I don't care, degrees or radians. Just make sure if your answer is in degrees, you include the symbol. If it's in radians, you don't have to include the symbol.
If it's in degrees, do we have to give an approximation?
Well, it would depend. Like if it was negative pi over 4, I would expect for you to put like negative 45 degrees. If it was like negative pi, then you could do that in degrees. But if it was some weird number, then you would have to approximate it. Yeah. All right, so part B. What are we looking for part B? How do I get part B? Magnitude? Just take the magnitude of the answer we just got.